So, imagine that we open the door. Describe the effectiveness of each of the forces regarding opening the door. As we know, the best scenario is going to be the farther away from the hinge that we are. So, this guy is going to be the easiest. This guy is going to be the hardest. So, the farther away we are from the hinge, the pivot point, the easier it's going to become. And also, the more perpendicular we are, the easier it's going to become. So, we have wasted energy in this case because of the component of that vector that is being directly parallel to the door. The perpendicular component is the one that is going to be used. So this guy here is all that we're getting out of that vector. So it is a reduced force that's being used for this F3 here, but because of the radius away from the hinge, it is still effective, just not quite as much. Okay, so that's what we're going to be talking about with torque in this section. So the ability of a force to use or to cause a rotation depends on three factors. One is the magnitude of the force, of course, the distance from the pivot point to the point at which the force is applied, as we saw with opening the door, and then the angle at which the force is applied. The primary angle that you want to use for torque is perpendicular. Anything less than perpendicular, and you're going to lose torque. Anything less than the maximum possible distance away from the pivot point, and you're going to lose torque. Okay? So we incorporate these factors into a single quality called torque, and we have this new Greek letter that we're going to be talking about here. This is the Greek letter tau, and you write it with sort of a hook shape and then a little squiggle on the top. That's actually a pretty good one right there. Just practice it a little bit. That's the Greek letter tau. So that is the rotational equivalent of force. So formulas that we have that involve force will have sort of a correlation from linear to rotational, and those formulas, the equivalent will use the letter tau. So in the figure that we have here, R is the distance from the pivot point. So we have the little hex nut here or bolt or whatever this is. The pivot point is at the center of it. The radius comes out to where the force is being applied. So this distance along that axis is the radius, and the force is being applied at this location here, not all the way out at the end. So it's important that you understand where the center of the rotation is occurring and where the force is actually being applied, okay? Now, we have a couple things going on here. We have the force itself, as you can see labeled here. So we have to figure out where the perpendicular force is. So that is perpendicular to the radius of the object that we're using. So in this case, the wrench. So we have to figure out the perpendicular force. And this is just as we've been doing for a while now. We also have a parallel force. That parallel force does nothing. Okay? So the parallel component does not contribute to the torque. We have to remember that. All right, but this is the parallelogram rule as we've been doing. So the perpendicular force up here, you have F sine, and then this Greek letter right here. Have we seen that one before? We talked about that one? I don't remember.
In geometry, I think we talked.
All right, so this is phi.
Yeah.
It does get pronounced both ways, but in mathematics, I believe it is pronounced phi most of the time. So we have F sine phi, P-H-I. Phi.
Wrong.
I'm wrong?
No, it's what it is. It's
Oh.
a little circle with
Yeah.
a line through it.
Yeah. Okay, so remember the radius is the distance from the pivot point at which the force is applied. That's the radial line. That's going to come into play here in a little bit again. The applied force is broken into parallel and perpendicular components. Of course, only F perpendicular contributes to the torque. And now we have this formula. Torque equals radius times F perpendicular. And that is also equal to radius force sine phi.
Why wouldn't you use theta?
So yeah, it doesn't really matter. Theta can be used as well. If you don't like using phi, it's fine. Okay. If you'd rather use just the same symbol every time, we like to use different symbols for different reasons. So in this case, because we're talking about something different than a regular angle for regular things, we're talking about rotational stuff, this symbol might be used for this reason. We use different Greek letters for angles when we're talking about a different type of physics. For example, we might use alpha when we're talking about flying angles, and beta and gamma. So this might be why. Okay. So torque that rotates the object in the counterclockwise, remember, direction is positive. Torque that rotates the object in the clockwise direction is negative. So this is the same as what we've been doing. We just have to remember that if we're talking about forces, we have to decide, is the force going to be positive or negative? So think about which way we're rotating or trying to rotate the object. If we were trying to turn this nut or bolt this way, then that would be we'd have to be turning this wrench that way as well. That would be counterclockwise, which means that this force would have to be positive.
They're loosening it now.
Okay? All right. Now, the line of action is something else that we need to talk about. So, the line of action extends in the direction of the force. So, our force is extending as we see here. So, that means we have this line of action here. Okay? Now, we could also use the line of action to calculate a torque. So the line of action extending through the force vector passes through the point at which the force acts. So we have the point acting here where the force is. Line of action extending through the force. Now we have a radius, a radial arm, the moment arm here. I just crossed that off, but I wasn't trying to. So the moment arm is designated R perpendicular and extends from the pivot point, and it crosses the line of action at a perpendicular angle. Okay, so it's making a right triangle with the radius and the line of action. And so the radius would be the hypotenuse then.
So then phi is equal to each other.
And so these are vertical angles here. So this phi is this phi, okay? We have a right angle down here. And now we have this right triangle sitting here. So now we have the moment arm between the pivot and the line of action. And now because of this right triangle that we've created, then the torque would equal R times F times sine phi, or we could write it like this. And because we have what I have in parentheses there, then we have torque equals F times R perpendicular. So now the torque due to a force with a moment arm would be this force. Okay? Torque equals R perpendicular times the force that's applied.
So that's at that exact moment.
As you see in the picture. And so that would depend on the length of the moment arm here and the amount of force that's applied.
So then your R perpendicular is going to get greater with the more the force is perpendicular.
The R perpendicular would get greater. It would get longer depending on the angle here. Okay? So if you were to turn this force so that it was applied this way instead, then that dotted line would be down here, and your R perpendicular would have to be perpendicular this way, right, to make a right angle like that. Okay? And so this R perpendicular line is just getting closer and closer and closer to the actual radius. The more you make the force applied, more and more and more perpendicular. Okay? So the greatest possible, basically what this formula is showing, is the greatest possible torque would be when the radius
equals radius perpendicular.
is actually, yeah, when this value here is when this radius, the moment arm actually becomes the radius. Okay? When
Because
this
when the angle
angle
is
is
90
perpendicular.
degrees,
Yeah.
and that sine equals 1, right?
Yeah.
And then
Yeah.
Yeah, you have the force and if R equals, yeah, I get it.
Yeah. Okay? All right, so both methods of calculating torque lead to the same formula. These are basically the same thing. So again, we have this guy. Phi is the angle between the radial line and the direction of the force. So no matter what, you can use either way. It just depends on the information that you're given in the problem. Just note that the torque is different from force in a very important way. Torque is calculated about a particular point. You got to remember that. You have to specify the point about which you're calculating your torque. So we're calculating the torque about the pivot point, wherever that pivot point is. Okay, it was the hinge in the door, or it was the bolt. Okay, or it was the, whatever, the axle or something. Okay, you have to specify that. So we usually calculate torques about a hinge, a pivot, whatever it is. All right. Okay, so it is hard to get going if you try to start your bike with the pedal at the highest point. So why is that? Let's try to picture that. The pedal on your bike.
Yeah.
So you have like the gear thing right here is the pedal. It's up here. So you got the pedal sitting there, and now you're trying to get it going. Why is it hard to get that going like that?
Because it's like
Because
the
you're applying
door.
force directly down.
It's
What
like
are you doing here with your fingers?
It's like pointed at each other.
It's like the
Yeah.
door, like when you're pushing directly on
Yeah.
the door.
So you are trying to push down, basically. You're trying to apply a force, but that force is down.
But normal force is kind of,
So what do you have to do to get that thing going?
angle your feet.
Yeah, you have to think about how to get this force to not be directed directly down. So there's a couple ways you could do that. Can you think about how?
Take it
You
backwards.
angle your feet.
If you lean back a little bit, you could angle your foot so that somehow you're getting this force to not be straight down anymore. And the more you can angle yourself backward or angle your foot, you can get that force to be a little bit tilted so that you can get going forward. And then once that pedal has turned a little bit, now you got a good shot at getting that thing to
Or
really
you
go.
could just like not be dumb and park your bike with an angle.
I guess there's that, yeah. So yeah, that's why that is. Okay. Your friend is trying to open a stuck door. He pushes it at a point 0.75 millimeters from the hinges with a 240 Newton force directed 20 degrees away from being perpendicular to the door. There's a natural pivot at the hinges. What torque is your friend exerting? And then name 3 ways you could suggest to your friend to exert more torque.
All right. I think we should draw definitely a free body diagram of some sort.
We could draw a picture for sure, and then draw a free body diagram. So just to visualize the door, we have a hinge over here. We have a door like this.
I'm not sure any of my friends would take any of my advice when they're trying to open the door. I know what they'd say.
Yeah. So what do we got?
Okay, so that distance is 0.75 meters.
So we're applying our force 0.75 meters from the hinges.
Yep.
Okay. So
Find a spot.
240 newtons. And this distance here is 0.75 meters. Oh, I forgot one thing. We're pushing at an angle. Does it say which direction that angle is?
20 degrees from perpendicular.
From perpendicular. Does it matter if it was 20 degrees out or 20 degrees in?
Now the force is going to be the same.
Doesn't matter. The force is the same. From being perpendicular. So 20 degrees is here.
We learned about 3069 to triangles.
Good. This is not one of those triangles, though.
I know. But next time we come across one.
Alright, so the torque. We can calculate that because we know everything. We know
Okay.
the radius, we know the force, and we know phi.
Yeah, we really know everything we need to know here. So next, we can go torque. We know the radius.
Sine.
We know the force that's applied.
Mhm.
And sine phi.
Phi equals 20 degrees, right?
So we know everything we need to know. So we have torque equals radius, 0.75 meters. Force applied, 240 newtons. The only question is this going to be 20 degrees that we use, or is this going to be 70 degrees that we use?
20.
Be the 20.
Is it 20 degrees that we have to use because it's adjacent to perpendicular, or is it 70 degrees because it's adjacent to parallel?
Draw your force.
If we go, let me go back to that picture real quick.
Oh, so we can
Maybe
use
this-
cosine 20 degrees, and then we both will be right.
So we want the perpendicular, right? Okay. So we need this one. Yeah?
Mm-hmm.
Okay. Our angle is here.
We'll draw your force all the way through,
Uh-huh.
like the line, and then you can find where phi is, and then it's just
Yes. Good. So we have to go all the way through. From the free body diagram, here's my point. The force would be on this side.
Yeah.
The 20 degrees would be here. And now we know that, which one is it?
It's the 70.
It's the 20.
Oh,
So it is the 20 after all. So we need sine 20 degrees.
61.56. So 61.6.
No, I'm sorry. It is not the 20. It is the 70. That's what I thought. So look at the drawing. We need the perpendicular. This is the adjacent. Oh wow, I'm an eraser. That's awesome. So here we are. Here we are. Okay. So here's the 20 vertical angles, right? Okay. And if I make my right triangle, this is the hypotenuse. This is the adjacent side. This is the right triangle. So that's cosine. So I would actually need the 70-degree angle right there to create. So that's the 70-degree angle right there. So this needs to actually be 70 degrees.
169.14.
Yep.
So 169.1. No, just do 169.
It's actually be 170 because we're only giving two significant.
Two significant figures makes it 170 newtons. So 3 ways we could be smarter about our torque.
Well, I can tell our friend, you need to go to the weight room.
No.
Oh,
Make your angle.
So
Make it.
push on it straight.
push perpendicular,
Go farther out. Push farther out.
push farther out. He's not pushing all the way out maybe.
Mhm.
Use more force.
Push harder, sure.
That means go to the weight room. See, what you didn't know is I was actually applying physics.
Oh, yeah, okay. All right, so that's 3 ways. That's good enough. All right, next. A wheel turns freely on an axle.
At the center of the.
So given the details noted in whatever figure, which one of these forces shown in the figure will provide the largest positive torque on the wheel? So think about it, and maybe we can eliminate some and come up with an answer.
Cool. That's what I
What do you think?
answered. A.
A?
Yeah.
A? Everybody thinks A?
Perpendicular.
All right. So
Maximum radius. Maximum force.
what do you think about C?
That's stupid.
Oh, why is it stupid?
Well, because you're not providing any torque.
All right, there is no radius from the center, so it cannot be C.
That's 0.
There's no torque. What about D?
No.
Yeah.
That is also 0.
Why is it 0?
Because
Because
the
it's not perpendicular.
angle is
The angle is not perpendicular
The
at
angle
all,
is
so
0.
it cannot be D.
sine 0.
What about B?
You have a radius, but you could go definitely a lot farther.
Yeah, your radius is half.
But
So,
Okay.
you're still
So what about A?
A.
well,
you're
yeah,
perpendicular.
the 2F plus
Uh-huh.
R, or times R. So that's 2FR
Okay,
times sine 90 degrees.
sure. What's wrong with F? Oh, sorry, E. I mean,
E?
Yeah.
It's not as much force.
not as much force.
No, that's still.
You guys all missed. We want a
Oh,
positive
man.
torque. And the
It
only
is
one
E.
that gives a positive torque, which means in this
It is
direction,
E.
is E.
It was a trick question.
It wasn't a trick question. You needed to read the question. These guys here give a torque this way, this way. Those are negative torques. So the only possible answer choice after we eliminate the ones that have no torque is actually E.
Oops.
All right, yeah, oops.
Interesting.
So you think that's Luis or Luis?
Luis.
Luis uses a 20 centimeter long wrench to tighten a nut, turning it clockwise. The wrench handle is tilted 30 degrees above the horizontal. Luis pulls straight down on the end with a force of 100 newtons. How much torque does Luis exert on the nut? What should we do?
Let's draw a picture of it.
Yeah, I want to draw a picture of this one first.
It's too much of it.
Okay, so we have a wrench. It's going to be an amazing wrench. And it's probably a hex nut, right? Or is it a square nut? It doesn't really matter. I'm going to draw a square
definitely
nut.
not a
I feel like a square nut this time.
It's not a square.
It's a square nut.
It's not a square nut.
It's a
Those
square
things
nut.
suck.
They do, and that's why it's a square nut. Okay, so now what?
That's a pretty good drawing.
Okay, then
Oh,
draw the little nut or the square.
I don't need to draw the nut.
Okay, you
We
just
got the
make it
wrench.
20 centimeters.
Now, at the center of this is the square nut. And I'm applying the force out here so that we have our radius.
Of 0.02 meters.
Okay, good. 20 centimeters turns into 0.02 though, 0.2 meters.
Yeah.
Right. Okay, and that's going from the center of the nut to where we're applying the force. And how are we applying that force?
Straight down.
Straight down. Okay.
I forgot the horizontal.
I did forget the horizontal. Okay. So from the horizontal,
It's 30 degrees.
we're going 30-degree angle. I'm really liking my drawing right now, except for what I just did with this angle. That's terrible. But I'm going to leave it. Okay. So we're 30 degrees above the horizontal. Luis is pulling straight down. So we have to draw that straight down. And this is what kind of a force?
100 newton
Yeah,
force.
100 newtons. So I'm going to label that.
and our answer is going to be negative, right? Because it's going clockwise.
Good. Remember, we have to think about what kind of a torque this is that we're applying. That force straight down is putting a torque this way. So we're going to have a negative torque. How much torque does Luis exert on the nut? Our
Well,
answer will be negative. We have a negative torque.
so we can, whatever that one is called, TU, whatever is equal to RF sine phi.
Now, with the information that we're given here, what we actually have is, if I extend this down, we have a radial, we have the radius going along the wrench, but we also have our perpendicular. We have a moment arm here. And what I've just created is a right triangle using the force. Okay. So we can use torque equals the moment arm times the applied force. And that makes this problem really easy. So be aware that your picture could actually reveal this scenario where you can really simplify the problem.
So we gotta solve for our perpendicular.
Yes, so we will use the right triangle to solve for our perpendicular.
So
Okay.
finding the adjacent.
100 root 3.
We're gonna use cosine.
We know 0.2 meters right here, so we'll use cosine.
I meant, yeah, sorry.
So this will be cosine, because we need the adjacent side and we know the hypotenuse.
So cosine 30.
So cosine 30 degrees.
Is equal to our perpendicular 1.2, correct?
Okay, so off to the side, I'm going to go, because I wanted to write that down, but we don't have it. So cosine 30 degrees equals the adjacent, which is our perpendicular, over the hypotenuse, which is 0.2 meters. So our perpendicular equals 0.2 meters cosine 30 degrees. Okay? So up here, our perpendicular turns into 0.2 meters times cosine 30 degrees. So we have torque equals our perpendicular, which is now 0.2 meters, times cosine 30 degrees, times the applied force, which is 100 newtons.
17.3.
So you got 17 point,
325.
okay, but it's actually a negative torque.
So it's gonna be negative.
So it's going to be negative. Significant figures would be 2. So we have 17.
Newtons.
Now, the force had units of newtons, but the moment arm had units of
Meters.
meters. So
newtons
this
per-
is newtons times meters. Torques are a force applied times the radius distance. Newtons times meters, newtons meters. So that's what we have. Okay, if you think about torques in your units that you're used to, foot pounds, it was always a distance times a force, right? Foot pounds. It's the same idea. Newton meters is what we get here. Okay, so negative 17 Newton meters tells us that we're rotating clockwise. Got it?
Yeah, I feel bad for that dude. He's gonna have a strip now by the time he's done.
Because it's a square nut.
Yes. People that use those nowadays are utterly stupid.
Well, maybe he got one of those fancy ones on one of those late night sales pitch shows that you see that has like the little things that pop in and out where it's like a ratchet. Those are real fancy and probably it worked really well for him.
I would just use a regular standard socket.
A standard socket,
Yeah, so like.
of course. But he got one of those on the late night sales commercials, infomercials, and those work great.
No, unless it says Grassman, it doesn't work great.